So let's quickly review what we have covered last week about XV6 boot process or boot thread. And as you can see from this figure, in the entry.s, it initialized the page directory table, which is named as entry pgdir. So this page directory table will serve as the virtual to the physical address translation for XV6 boot thread. Right after setting up the entry pgdir, it set up the kernel stack in the entry.s. The reason it set the kernel stack is right after this initialization, the boot thread will invoke what? The C routine, which is a main. All those C, execute the C subroutine, we need to have stack.
Yeah.
So that's the reason why in the entry.s it set up the kernel stack. After that, it jumps to the main, right? And the kernel boot thread using this kernel stack to execute all the subsequent C routine, right? And eventually it gets to where?
The scheduler.
No, not before that. Before that.
The user in it?
That's right. So after the initialization of the memories and I/O devices, do you know what is a PIC stands for? Before we get to it, we will cover this one later. PIC stands for the Programmable Interrupt Controller. Okay, and there are programmable interrupt controller for every CPU. So CPU cannot directly talk to the I/O devices. So programmable interrupt controller has several ports. Whenever the external I/O devices generate interrupt, certain pin voltages might be lowered or getting higher. And this PIC is a program such that it informs the CPU, you have an interrupt. So it's a kind of delegate. Do you know what is the next one? IOA PIC? APIC stands for Advanced Programmable Interrupt Controller. So in short, in modern computer has quite complicated I/O device hierarchies because some I/O devices slow compared to the others. So they have the programmable interrupt controller has some hierarchy. Yeah. So far so good. So I will briefly cover all this. UART in it. You should know what is a UART.
UART. It's
Yeah.
I know what it is, but I don't.
Okay.
I know how to use it.
So when you use this UART, this is a serial for RS-232,
Yeah.
right? So what is universal, asynchronous, something, I don't know, I forgot UART.
Yeah.
And
I don't know what it stood for.
thread vectors and buffer cache in it, file in it, the disk in it, then start others because the model of this XV6 targeted for dual core system, right? So it start others, and then finally it gets to the user init, right? So can you tell me what happens inside of user init? Let me help you, okay? Let me jump to that routine, user init. So this is a routine, alloc proc. What's happening in the alloc proc? You see this figure? You see this figure on the bottom? In the proc.c, you will see the p table global variable, which is a static global variable, which is only relevant within the file proc.c scope. How many entries in this proc array? There are 64 entries in this proc array. What's the data structure for this proc array? Right, struct proc, right? So there are 64. So let's see what's going to happen in the alloc proc. Do you remember what happens inside of alloc proc? So alloc proc return what? One pointer.
Yeah.
Pointer to what? One of the entry in p table proc array. So it pick whatever available process control block and return the pointer to from the alloc proc. Okay? So let's get inside the alloc proc. As I said, the main part is what? Iterate over p table proc as long as P state is not used, and return that pointer, but before it pointing, it initialize this data structure. Initially, make the state as an embryo, and assign the PID as next PID. Do you know what is the next PID? I believe it is initialized as a 1, I believe.
Yeah, it's just a counter.
Right? So counter. So the first user process will be what? Process ID is 1, right? After that, it allocate the calloc. Calloc will return 4 kilobytes of buffer from the kernel space. Okay? And then initialize this K stack. What is this? This one. Okay?
Stack point.
This K stack will be initialized as 4 kilobytes of buffer, which is returning from the calloc. So far, so good? If this is successful, then set the local variable SP, the PK stack plus K stack size. So where after this statement, where SP is pointing? Here, right? You see this top? SP point this top of this kernel stack, but plus 1, right? 1 above. Okay? After that, leave room for the trap frame, because this kernel stack will be being used to secure the data structure trap frame. Why? Do you know why we need this trap frame? Because the user process we try to create may have the system call. Right? If this user process invoke any types of system call, or any types generate any types of interrupt, then kernel needs some space for the trap frame to save all the motion state in the user space. That is what this kernel stack for, and that is what the reason why it secure the place for this trap frame. You see this kind of curly space, curly arrow? I marked as a trap frame. This is the size of the trap frame. Okay? So let's look at the data structure of the trap frame. This is the data structure of the trap frame. EDI, ESI, EVP, OESP, right? This is the name of the field. And this stack pointer local variable, bring it down by the size of the trap frame. I want you to pay attention about the way that I label. Where the EDI point place in the stack, in this stack. EDI is right here, bottom, right? But EDI appears on the top in the trap frame. Why this is the case?
Little India.
Right, because X86 is a little India. What's a little India? Byte ordering.
Yeah.
The most significant byte appears on the high address, right? The least significant byte appears on the low address. Let's look at this data structure. Which one appears first? EDI, right? So EDI should occupy the most least significant byte address. So that's the reason why EDI appears on the bottom. Okay? Right? May I move on? Okay? Right. What did I do? Oh. Huh. Yes. Okay, good. Right. And then PTF is initialized point, is whatever SP points to, right? At this point, this trap frame pointer being initialized point, this particular SP. May I move on? May I?
Yep.
After that, SP is decremented by 4 and store the address of trap return to this particular slot, which being pointed by SP. So this particular slot of the kernel stack being initialized with the trap return. Good? So yeah, are you guys excited about what's the effect of the C statement? This is so cool, right? Next one. SP is a bring it down, this pointer bring it down by the size of the context. This is a trivial C question. I'm pretty sure if you have some chance to interview with a company who are asking you whether you know how to write a C code or not. And this is kind of not a popular, but this is another well-known question about testing your understanding of C operator precedence. What's the asterisk? This is known as a dereference unary operator, right? What is this right arrow?
The right arrow?
Yeah, what's the name of this right arrow? This is what? It's a field operator, field access operator, right? So which has the high operator precedence? Which one has a high operator precedence? The reference operator or the field access operator?
The field access?
You're right. Field access operator has the high operator precedence. What's the data type for the P context? It's a pointer to the struct proc, right? A struct context. So if you put the dereference, then it will actually ask you for the size of the struct context. Okay? So bring it down those amount of data structure for the struct context, and then it initialize P context to what? The pointer to the SP, this address. So the context pointing this particular place in the kernel stack. All right? And then P context EIP. P context EIP, this field, being initialized with what? Address of fork return. And this initialization of the first entry in P table proc being initialized in this manner, and then pointer to this entry being returned from hello proc. So far so good? So far so good? All right? After that, init proc be set to P, PGDIR, set up the KVM. Okay? What's the setup KVM routine does? Oh, by the way, what's the PGDIR? Right there. This is the page directory table to translate the user address space for this particular user process to the physical address. Every process must have its own page directory table because each virtual address per user process should be able to map to the different physical location in the physical memory. Therefore, every process must have distinct page directory table, except one, kernel address space, right? Because we only have one copy of the kernel, so kernel address space needs to be shared. That's what the setup KVM does. We already create the space for the page directory table, but we haven't initialized yet. So let's look at the setup KVM. Okay, go through this XV6 boot thread page directory table and initialize this page directory. All right. So whatever this process maps to the kernel address space, that address is the same for all user process it will create now and future. Why? As long as they invoke the setup KVM, simply copy those entry in the page directory table from the XV6. This boot thread will be copied over the user process page directory table. As I said, why? Because every user process, they share same virtual address of the operating system x86. After that, init UVM. Now this is kind of interesting part. Mark the PGDIR by copying this binary init code start and binary init code size to this page directory entry. In this process, what actually they did, let's go to the init UVM. Not only they initialize the page directory table, but also they physically move that memory location, which is pointed by what? Binary init, I forgot the name. Binary init code started the symbol table, and they move this memory block. They copy this memory block to where? Starting from virtual address 0 up to whatever page size, which is a 4 kilobyte. Okay? And then they also what? Initialize the page directory to map this virtual address to the physical address after the copy. All right? And then they do the mem move, and then they initialize all those PTFCS. When you do this, which field will be initialized? PTF, right? This one, trap frame. Where's the trap frame? I believe this one, right? This is a trap frame, right? This is a base address. And CS, where's the CS? Right here, this field. This being initialized by set U code shifted by left by 3-bit, ORing with the DPL user, which is a protection level. And these are the way initialized. This statement will directly initialize somewhere in this trap frame for the kernel stack prepared for the first process. Can you follow me? Right? So E flag will be set to FLIF, which is enable interrupt, something like that. TF ESP as a PG size. This ESP will be set as the PG size. EIP is set to 0. Which one is that? This, where is the EIP? This one, right? This particular field being marked as a 0. Okay? After that, make the safe string copy. So this P name being initialized as the name of what? Init code. After this preparation is done, make this state as a runnable. So far so good, and then return. That's what the user init does, right? That means, let's look at the P table proc. From the user init, this first entry of this proc array being initialized in this way, and mark this particular process control block as runnable. Because even in the user, let me look at the part 2. You may see better. So this is the actual changes after the user init. Right? So I hope this makes sense. Init code.s. This code, init code.s being assembled and linked, that images will be copied to this, starting from the virtual address 0. Right? This is a location of binary init code. Yeah? That will be placed in the text section of the user space. Okay? All right? All right, so what's the next one? XV6 boot thread is about to execute np main. So far so good? So let's go to the np main. I just keep doing this one.
NP means at the bottom of your kernel?
Yeah, this one, right?
Yeah.
Oh, right here. So IDT init, and let me tangent a little bit. Do you know what this IDT stands for? Interrupt descriptor table. Okay. Initialize the interrupt descriptor table. Okay. So when I taught this class about 2 years ago, and while I'm moving along this routine, I try to detail what each routine does, but I realized this explanation adversely impacts your understanding. So for the time being, I'm going to abstract it. Okay? And then jumps into scheduler. At this point, you should know what is a scheduler does, right? In the proc, that's it. Right? So what's the lesson? XV6 boot thread complete its preparation for the first user process, And then this boot thread turns into the scheduler thread, kernel scheduler thread, and it remains in the system until during the lifetime of this operating system. So at least there's one kernel thread, right? This kernel thread will serve as scheduler. Okay? When I cover this lecture, like first or second lecture, the operating system is running as what? Extension of the user process. Right? Whenever user process make the system call, then that's a point of time. But user process privileges elevate as the kernel privilege and running the kernel code. In other words, the kernel is running as an extension of the currently running process. But let's look at the XV6. There's a little one exception. That's still same, right? Whenever the user process make the system call, then the kernel is running on behalf of user process that invoke the system call. This remain as true, but there's one exception. For this XV6, there's one kernel thread, resident kernel thread, that is a scheduler. Okay? This boot thread turns into scheduler thread, and it remains in this XV6 lifetime.
Yeah.
Okay? So far so good? So let's look through this scheduler code. I'm going to cover all those locking and enable interrupt and disable interrupt later. All it does was what? It goes through what? Process table. This one, this array, and then pick what? The first runnable state. Once it finds it, obviously the first process was marked as runnable, so this process control block, which we already initialized, will be picked. Right? And then the P being set to the prop and switch UVM. What is this P? From this point on, this PGDIR, this page directory table pointed by this particular PGDIR will be used by the CPU as the what? Virtual to the physical address translation. The reason why, after switching this page directory table, the reason why we can confident the next statement still be valid, because kernel address space will be identical to all the rest of the user process. As long as kernel address space is concerned, there's only one copy, therefore all those high address will remain identical in the page directory table. And P state, mark P state as running. It used to be runnable, right? This one is marked as what? Running. And then this is notorious, but at the same time, famous SWTCH, which is context switching. Okay? Can you see this one? SWTCH is forms of what? Function call. So this P context, this argument will be pushed to where? Kernel stack of XV6 boot thread, right? I don't know where the location of the stack pointer, but before this call, P context will be pushed onto what? Stack top, right? P context. This is the second argument, followed by CPU address of CPU scheduler. That is, the first argument will be pushed to the stack top later, and then make the function call SWTCH. But remember, whenever you have a function call in C, compiler will translate this function call such that what? Push the return address to the stack top. This EIP will be initialized, this field EIP will be initialized as what? This address, switch KVM. Because after the SWTC, you need to come back, right? And then resume the execution. So this EIP will be initialized to the address of the beginning of SWTCH KVM. Make sense? Mm-hmm. And then jumps to SWTCH. Isn't it amazing? Right? Just how many instructions? I mean, it's less than 15 machine instructions achieve context switching. You heard about it? Now this is the actual realization of context switching. Let's see. Move L for parenthesis ESP %EAX. What it does? Load this address of CPU scheduler to the EAX register. This is a load instruction. You know that, right? Move L ESP offset by 8, which is the value of this P context will be loaded into EDX general purpose register. So EAX hold, second argument, EDX hold, first argument. Oh, no, I'm sorry, second argument. So EAX hold the first argument, and EDX hold the second argument of the SWTCH. Push L, EBP, push L, EBX, ESI, EDI. You see there was EBP, EBX, ESI, EDI being pushed on the stack top. Why they do not push EIP? Because EIP, EBX, EBP, EBX, ESI, EDI are the struct context, but they didn't push the EIP. The reason is SWTCH is a function call. It will push the return address anyway, so there's no need to push the EIP again. Clever? Clever? So now, whoever writes this XV6 operating system, he knows. I'm pretty sure he spent many hours debugging. I can see his or her sweat and agonies while they implementing this operating system. Even though it is quite compact, but I can see their efforts. After this one, the kernel context being saved for XV6 boot thread. Why do you need to save this kernel context? Without saving this one, after performing context, then some other process will start running, right? Without saving this one, there is no way it can come back. So before give this register for other processes use, it's better to save the current machine state for this XV6 boot thread in known location for this particular kernel, right? And give this register to the other processes execution and let them run and then come back using this, restore the context using this information. How? As long as we know where this ESP is pointing to, then we always can come back and restore the context for this XV6 boot thread. Right? Okay. And then here's a couple of statements, which is the switch step. Move L ESP to the EAX. Current stack pointer ESP will be saved where? Address of the CPU scheduler. This is the well-known location where this ESP will be stored, saved. Save the current stack pointer to this location, and then reinitialize ESP to the EDX. What's the EDX? P context. Okay. What's the P context? This one. And this ESP being set now. It's a totally different one. Okay. You are in United States. After this stack swapping, then you suddenly discover yourself in South Korea. Seriously, right? Mm-hmm. Seriously, that's what the stack switching does. From this point on, let's see what happens. After this stack switching, what's the next thing? It recovers the kernel state, this kernel context, and start pop L, EDI, do the reverse action of the pushing. So EDI recovered, ESI recovered, EBX is recovered, EBP being recovered, then return. What does the return do? The return address can be discovered from the stack top, which is a fork return. Isn't it clever? Isn't it clever? So let's go to the fork return. Okay. It does some other stuff if it's a first, but basically what? It return, right? Immediately after return. What's the return? Return address will be here. Trap return, right? This is the return address, right? After the fork return, right? And then you will hit another return. Another return will be the stack top, which has the return address. We initialize the trap return. So return address is a trap return. Let's go to the trap return. Pop all the general purpose register, which is EDI, ESI, EBP, OESP, EPXE, all those general purpose register being popped. In other words, the general purpose register being initialized with all those memory content on this particular trap frame. After that, GS register being initialized from the content of this stack. FS, ES, DS, right? And then skip over trap no error because we don't need it for the time being, right? This first user process, we try to create this first user process, right? Skip over, and then ESP is pointing right here, right? And the rest of the memory location will be restored as a machine instruction, x86 machine support. So at this point, when you do the I return, this CSE flag ESPSS being reinitialized by what? x86 CPU as a one machine instruction. Okay? Now you remember ESP being set to 4096. This is the current stack top at the user space because the virtual address begins at what? From 0 up to, right? Begins at the 0. So 0 holds the first user instruction, and stack top is 4096. Okay? So far so good? Okay? And after the I return, now the CPU starts fetching the instruction from where?
The VIP.
Right. So this first user process init code start running. Isn't it amazing? Isn't it amazing? Are you excited? I was excited. So this is the creation of the first user process in x86. This is not much different from Linux. Why Linux is so huge? It also has many state-of-the-art algorithms to make the operating system perform better. But the other reason the size of Linux is getting bigger and bigger is device driver. It tries to support many different plethora of I/O devices. And all those device driver is somehow kind of sucked inside as the size of the Linux. Okay, but now we don't have many I/O devices, so this XV6, the size of the code relatively small, less small, but the way it creates the first user process remain quite similar. So if you understand the user process creation process in XV6, it's much, much easier for you to understand how operating system, such as Linux, the boot process of Linux operating system. Okay? So let's start executing this init code. Where is the code actually you can find? Init code.s. Right. Yeah, this is init code. Okay? So this is the entry point. Okay? It pushes the ARGV. You see the little thing? ARGV stack goes downward, right? Mm-hmm. So person ESP point, whatever, the top of the stack, one above, whatever the 4095, so 4096, ESP point here, and then it pushed the ARGV to the stack top, push L $init. This is the code, address of the code to execute later, okay? You will see init and push L0. You see this one? So these three arguments is pushed to this whatever area pointed by this ESP. How do I know this ESP is pointing initially 4096? Because before we made the I return, from the trap return routine, the ESP being initialized as 4096. And EIP was initialized as a 0. That's the reason why we know the CPU fetched the instruction from the address 0. Okay? Right. And then after pushing all those arguments to the stack top, so after this one ESP point, here right? Do you know what does this do? This is system call, isn't it? So sysexec is placed into the EAX register. So the kernel will recognize what types of system call being made by inspecting the value of EAX register. You know that, right? After initialize this EAX register as a sysexec, then invoke what? syscall. You should know what the syscall does. When this syscall being made, what happens? Because the user process try to execute the privileged instruction, so this will generate interrupt, right? The police got the ticket for you, right? And then at this point, the user process's privilege getting elevated to the kernel mode, right? And then kernel address space start opening, and then it start servicing this particular syscall at the kernel address space. Using what? Using this kernel stack. So far so good? Using this kernel stack. So let's go there. So what's the entry point in the kernel to service this syscall? What is the name of the routine?
Exec?
No, for this exact system call, right? There's only one entry point in the kernel. So what's the routine name to handle?
The trap?
Right, so let's go to the trap. Right, this is trap routine. All the syscall comes here, right? TF trap no is a T syscall. Proc TF to the TF, okay? So how this TF being initialized? It should recycle this one, right? Before it gets to this trap routine. What is the entry point? All traps, which is another assembly code. You want to go to the all trap?
Oh, yeah.
Right, so this is the place. Right? Push LDS, ES, FSGS, because this trap frame is already being initialized, right? For this process. So the CPU knows where this SS, ESP, flag, CS, EIP being flushed to where. How it knows? It used this trap frame pointer, it initialized right there. And then push LDS, all those things will be spilled to this kernel stack, right? And let's look at the right before the trap. The first argument is what? After spilling, and then this ESP being pushed to where? As an argument for the trap routine, right? And this trap being invoked. Okay, so this is the entry point, right? And then proc TF being reinitialized as whatever TF, which passes an argument. Okay? Right? And then invoke the syscall. So here's a syscall. And we know what syscall was made? Syscall exec, right? So we need to go to where? Sys exec, I believe. So this is the system call being triggered by the exec system call. So I don't want to go through this detail, right? But have some feel for it, okay? And when it completely exec, do you know what happens? This address space that you have is wiped out by the executable of this path, and this executable will run with whatever ARGV is passed as an argument. So initially, this address space has the code for binary init code, right? As soon as you does exec, what happens? What happens? Whatever passed by this path as an argument will be replaced, this text section, with the whatever executable of this path, and ARGV, and run this executable pointed by this path will start executing. You remember? Fork followed by exec, right? Fork is what? Create, copy the address space. It basically clone, right? Then immediately after the exec, the existing address space is replaced by the whatever argument you pass as an exec. This is not copy, actually. The executable file being used as an input is start building up the executable image in this address space. So it needs to parsing the ELF file. Okay, it's not simple copy. So it does some special action of the ELF read. ELF, do you know what is an ELF? Let me just write it here. So ELF is one of the binary file format, right? This simply binary file format does not mean this is an executable, right? Actually, the one who start building executable, there's an ELF reader. ELF reader will read executable file and create executable images in the known location of the physical memory. I don't want to get that deep, but for the time being, what you need to remember, exec will replace whatever this user address space with the executable passed by this path and run this executable with the argument that you pass as an ARGB. Okay? So what's the code after this exec execute? So let's go to the init. I believe that's the actual code. Yeah. Oh. Init.c. Okay, this is a routine. So this main start executing after the exec. How many processes in the XV6 so far? How many? At this point, how many user processes running?
We're running a net, just a net so far, right?
Right.
So
Yeah, so far only one user process, right? One user process. Agree?
Yeah, we're about.
Right, we are about to run. It used to run the init code, but init code does the exec. So this first user process's address space is wiped out with the what? This main routine, and then this main routine start execute, right? It use open system call, dup system call, and dup system call, followed by what? This full. Okay, so init will remain in the system as the first user process forever. Okay, why? How can I tell? Because this is an infinite loop, right? And printf, init starting. So I hope you have some familiarity about these messages at this point. Mm-hmm. If not, then something wrong. And then right after that, PID, fork. Right? So can you tell me what does the fork do? Tell me, any expectation what's going to happen?
Create another process.
Right. How?
By copying the stack.
Copying the stack? Right. Only the copying the stack? Okay, so let's go to the fork, right?
Okay.
Okay?
Yeah.
So you're right. I mean, it just cloned the address space of the current running process, right? After this fork, we have one more user process, which is the child of the currently child process of the process that made the system call fork. So let's look at the code for the fork. Okay, it's a system call, right? Allocate process. Alloc prop. What happens? Tell me what happens in alloc prop.
Basically initializes the process.
Okay, so it goes through this p table, right?
Yeah.
And finds some available process control block in this array. Obviously, the second one, right? And then it marked the p state as embryo and PID as next PID. At this point, PID for this process will be 2, right? Because the init was 1. And it allocate the k-stack, hello. So as a result of this one, you see this space, right? This stack will be prepared for the child process. and then SP being set for the P K stack size. So this is the same process, right? So let me show you what I meant by. Make sense? So we have this second structure process control block from this array, and all those page directory, K-stack, all these pointer pointing to this newly prepared kernel stack. Okay? So can you tell me what's going to happen after this alloc proc being completed?
Then it,
So let's first look at this K-stack. Where this K-stack will be pointing to? This is a kernel context, right?
yeah.
Yeah. Because
Yeah.
this is the area in the kernel stack to hold kernel motion state for this particular user process, right?
Yeah.
What about the context? Oh, wait a second. I'm sorry. I made a mistake. I believe I made a mistake. The K stack is, okay. I made a mistake. K stack should point where? The base here, right? And this context should point where? It's a spaghetti code, but you know what I'm talking about. This one. This is a kernel context. Now, what about trap frame? Where this trap frame should point? May I? It looks like a spaghetti code, but whatever the field for the EDI. So this is a place, this trap frame being initialized. Okay? All right, and then this state will be marked as what? Runnable. Right? But for the time being, the first user process is marked as what? Running, right? Right?
Yep.
And mark this one as runnable and return. Oh, please. Return P. And then a copy of VM. Please read through and you will understand what did I meant by the clone, the parent process address space to the child process. Everything is copied bit by bit. Okay? Whatever the parent process has, the content of this address space is copied over to the child process. It clone, right? Until it exec. And NP parent, this parent, where is the parent field? This parent field will be point the parent process, which is a proc 0. Okay. And clear EAX, so EAX register. So this is the initialization, right? And mark the NP state as runnable. So this is a routine for fork, okay? After it returns from the fork, now you can see the exec, right? If happens to be after the fork, and if the return value of the PID is what? 0, that means it's a child process, then it immediately execute what? Exec sh. So that this second user process is launching as a shell process. Okay? All right. Why I'm doing this kinds of thing? The reason is every user process, it has its own slice of CPU time, quantum. Whenever the timer quantum expires, right? Then here it goes. It goes to the trap routine. And if the timer expires, then the process interrupt controller, in other timer will lower the voltages or raise the voltages on the process interrupt controller block. Programmable interrupt controller certain port. Then CPU recognize there's a timer interrupt comes in. And this is a routine. The trap will be invoked to handle that particular timer interrupt. Okay? So let's see the timer interrupt. There are two times. IRQ timer. Whenever you see the IRQ timer, that means there are interrupt comes in from the timer. So let's look at this time. CPU num is 0. You may wonder what this routine does. And this particular case entry is designed to handle the sleep system call. Do you know what is a sleep system call? User process can issue some system call, I want to sleep for 5 seconds, something like that. Right? So argument of the sleep is what? Number of seconds it would like to sleep. Whenever those sleep system call being made, and that system call being handled by this case entry. All right? However, if there is some general timer interrupt comes in, unless the process is not waiting on this sleep channel, then where it goes down? It goes down there. Here. This way. Okay? If the trap no is equal to IRQ timer, if the proc state is running, does it familiar to you? Yield. Who does invoke the yield? Actually, the currently running process invoke the yield by itself, but those yield being made as what? As an extension of the kernel. Right? So let's see what happens in the yield. Okay, for the explanation's sake, let's assume that this init process, init is still running. Okay? May I? And when this comes, and let's say the first user process invoke the yield, then let's see what happens. Mark this proc state as runnable. Okay? Where it goes? Here it is. Okay? And then invoke the scat, right? Please. Let's go to the scat. And I want you to pay attention to the SWTCH. Okay? What happens? What's going to happen?
Does the context?
Right. So context will be what? Let's say this is the current stack top, right? Right? So here, CPU scheduler will be pushed first, right? Are you with me?
Mm-hmm.
Right? And address proc context. Right? Where is it? Where's the address of proc context? Can you tell me? What's the proc? Right now, proc being set for this process control block, right? So proc context means what? This P context. This area. It referring this area. You see that? Right? And then SWTCH. Let's see what's going to happen in SWTCH. What did I do? So what happens? What happens? Can you explain to me what happens? So what's the value of EAX register? This is a load instruction, right? So right now, as a result of this pushing, also there's a return address right here, right?
Yeah.
So what happens? ESP plus 4, right? That is, ESP being bring it down, so that refer the address of proc context will be loaded into the EAX register. And what else? ESP plus 8, which is the CPU scheduler, will be loaded into the EDX register, right? Right? Push EL, EBP, EBX, ESI, EDI. I guess I made a mistake. I think I made a mistake. This ESP should somewhere here, okay? Okay. Let me just wipe out this one. After pushing the stack pointer, after pushing all those trap frame data structure to the kernel stack, I'm pretty sure ESP point right here. Okay? So I do not want to make the mistake again. So let's start from this particular SWTCH again. Okay? CPU scheduler being pushed where? I think this ESP being used. I'm pretty sure because the trap frame, this one is being passed. So let me a little bit, okay, I would like to little bit, I cannot precise on this one, but ESP, let's assume the ESP point somewhere here, okay?
We
Right?
can like abstract it.
That's right, let's abstract
End
it,
of
right,
the
abstract
application,
it,
right?
okay? And the first argument, the second argument, CPU scheduler being pushed to whatever the stack ESP points to and bring it down. And then first argument, which is the address of the proc context, which is this particular address. The proc context, which one is it? This context, right? This context being pushed as a second argument, okay? And then called the SWTCH. I try to be precise all the time, but somehow I'm just losing the track of the pointer. So now I need your help. So ESP plus 4, that address content will be loaded into the EAX register. What is it?
The proc context.
Proc context?
Yeah.
You sure? Right. Address of the proc context. Address of the proc context will be loaded into EAX register. And then CPU scheduler is loaded into EDX. What this location holds, do you know? So if you go to CPU scheduler, what information this memory address holds? That is this address of ESP. Okay? So this is the stack switching again. Right now, they try to stack switching from this ESP to this ESP. But before it make the stack switching, it need to save this ESP to where? The kernel context.
Yeah,
right, kernel context. Okay, good. All right. After that, it pushes EBP, EBX, ESI, EDI, I believe this location. It saves the current running state of the kernel on behalf of the first user process being saved in this area, and then it performs the stack switching. Save the ESP to whatever EAX being points to. After that, EDX, this ESP being reset for the current ESP. After this point on, this kernel stack being used for the CPU's execution. Let's see what happens. Okay. As soon as this ESP being set, then what it happens? Pop L EDI, EDI being recovered, EBX, EDI being recovered, ESI being recovered, EBX being recovered, EBP being recovered, right? And then return. It pick whatever EIP value being used as a return address. Where is it? Where is it? Yeah. Switch KVM. This is a return address. After it return, then it goes where? Switch KVM, switch to the KVM, whatever entry PGDII, for this kernel scheduler thread, right? And then initialize the proc to the null, goes to where? Jumps to the P++, increment the P++. You remember what was the value for the P? It was the first address, right? First entry in P table. That's the point of time you perform the context switching, and this user process starts running, and it forked the child process. It's long way back, right? Long way back. Now, after the stack switching, the kernel come back to this switch KVM, the beginning of switch KVM. It started executing. We set the proc to the null. It jumped back to the P++. So now, what's the P points to after the increment, after this post increment? Next one. Right. So it check whether P state is runnable, which is the second process, user process you create. It marked as runnable, right? So what happens? It starts running the second user process. If the timer expires, what happens? What happens? You know what happens?
It will switch it. It will swap.
Right, it stack switching happens amongst this kernel thread to whatever user process picked as runnable. Then that user process, after the stack switching, this user process return from kernel space to the user address space, run for a while. If the timer expires, then it goes to the trap routine, and then the kernel will invoke the yield on behalf of the user process. As soon as the yield being invoked, then scad routine will be invoked. Scad will does stack switching again, and kernel context being recovered, and resume execution from switch KVM again. So now, here's the deal. When you set the GDB as a breakpoint after the SWTCH, if you put the next, what's going to happen? It may get to the SWTCH as a next statement, but there are a lot of things happens. Lot of things happens. World has been changed. You have some lapse of time, right? You felt after the SWTCH, everything is just remain identical, but there are a lot of side effects happen. It's much more onerous than you can possibly imagine. Okay? Maybe someone died in between. Seriously. Maybe you guys can get married and have some babies. Suddenly, is it right place that I'm in? Something like that feeling, okay? This is the context switching in XV6. This one is not much different from other contemporary operating systems. Any versions of Unix-like operating system. This is the way the scheduler is working in modern operating system. You heard about it, and I'm showing how it works. Okay? That's the reason why debugging the kernel is so difficult, because the timing is so sensitive. So far you ignore the timing constraint, right? And you talk about multi-threaded application, right? Whenever you're dealing with a multi-process or multi-threaded application, the debugging is quite difficult, because you cannot gauge when those threads start executing. You cannot predict anything, right? You cannot. You shouldn't, right? Mm-hmm. Same story applies in the operating system kernel. Even though it's a single CPU model, we also need to deal with the timing of all those interrupt, which is the external event triggered with the I/O devices. We don't know when those particular interrupt comes in. We cannot assume that. If you assume those kinds of timing, then that operating system has no value. It's quite onerous. And I try to explain how difficult to teach operating system to many people around. They still believe teaching operating system is the same as teaching software engineering or something like that. And this is much more onerous, because they do not understand how much effort it requires as an instructor. And I really wish someone can recognize how much efforts that I need to teach this class, but unfortunately, not many. Maybe there are some, but not in this campus, as far as I know. Okay, that's all I have. Okay, yeah.
So this may be a dumb question,
Yeah.
but how do they decide what a good ratio is between letting the process run and
Okay.
then switching it? Because obviously this takes time to
Right,
do all
so
this.
usually the modern operating system, they give about 10 milliseconds as a time quantum.
Okay.
So that is kind of general trend. Why they select as a 10 millisecond? The reason is the context switching by itself has a lot of overhead.
Yeah.
It's not simply switching the CPU. There are cache issues, there are TLB issues. I will cover this one. Actually, I already covered the TLB, right? Translation leukocyte buffer and the cache.
So
These,
like,
yeah.
how long does that whole process we just walked through take in like,
Oh, this one is quite fast.
okay.
This is quite fast. And whenever you have a system call handle, such as scheduler, this should complete as fast as you can. Right? If you have C printf here, so stupid. And if you try to debug this one by placing the printf or C printf, this is treacherous. The C printf is write, okay? This is write system call, not the system call write, like an IO device kind of request. Whenever you just leave the CPU, the order of magnitude for the timing is just about 100 times more. Okay? So this is not the right place to debug with the C printf. Okay? Anyway, so that's all I have.
Oh gosh.
Yeah.
Yeah.
And I'm going to give another assignment this Thursday. I'm currently working on it. So hopefully you guys have some understanding how onerous it can be. But at the same time, it is quite exciting topic.